We're ready to start. So first talk from Alisa, who's going to be talking about preprocessing-based verification.
Oh, hello. I will talk to you about verification of secure multi-party computation protocols in this talk. And first of all, let us recall what is a secure multi-party computation. So suppose that we have some parties. In this example, and throughout the presentation, we have 3 parties. Let us call them Alice, Bob, and Chris, just some abstract parties. And what they are doing, they have some inputs, x, a, x, b, and c. They compute some function f on these inputs, and they obtain some outputs, ya, yb, and yc, respectively. And how do they compute f? They perform some local computations with their inputs, and they can also exchange messages that they can in turn use on the next rounds to finally compute the outputs. And what can these inputs and outputs be? So one possibility is that each input is a private input of each party, like XA is private data of Alice, XB private data of Bob, and so on. And for example, finally, it may happen that each party gets the same output. Like in this example, the answer is yes. And maybe this private data is some bank account of each party, and they check how much money they have, sum each up, and they check if they have enough to buy something big, like a house. So the answer is either yes or no, just a single bit. And no other information should be leaked to any of the parties. It is also possible that the parties are just computing parties. They do not provide their own inputs. Instead, they use the inputs of some other parties, even more than 3, maybe a bigger number of parties. And these inputs are shared among these 3 computing parties in such a way that no party can derive anything about the secret themselves. And again, similarly to inputs, the outputs can also be shared in such a way that no party knows what answer is. Of course, the answer yes could not be shared character-wise, like on this example, because it is important that no single party can know whether the answer was yes or no. And finally, these outputs can be delivered to some other result parties who can reconstruct the secrets. So there are different ways how you can use the secure multi-party computation. So let us just think that it doesn't matter whether inputs are private inputs of the parties or they have been shared by some other input parties. So we just have 3 computing parties. They have some inputs, some outputs, and compute a function f. So what happens here? The parties do some computation, and for this they need to exchange some messages. And the description how exactly they compute and exchange these messages are defined by a protocol that the parties compute. So a passively secure protocol means that indeed no party learns anything that it is not supposed to learn about the private data, as far as all parties follow the protocol. Then everything is fine. And the computation is indeed secure. No information about private data is leaked to any of these parties. But in practice, it may happen that some party becomes malicious, in this example Alice, and it starts cheating. And instead of sending valid messages, it sends something bad, some dangerous things. And of course, one bad consequence is that the outputs are no longer trusted. So the output is wrong and correctness is suffered. And even worse, something may happen on this movement of the other direction of these messages. And it may happen that the secrets will leak to these actively corrupted parties. And in this case, Alice can reconstruct the private data that it was not supposed to learn. So in practice, we would like to have protection about these actively corrupted parties. But the problem is that indeed there are protocols, but usually they are much slower than protocols that are secure just against passively corrupted parties. And for this reason, there are some intermediate classes like covert adversary. This adversary will not cheat as far as it will not be caught in cheating. And usually these protocols are faster than those that are secure against active adversaries. And this motivates building a verifiable multi-party computation. So let us first run the passively secure protocol and then verify it in the end. So in this paper, we are dealing with a verifiable multi-party computation with honest majority. And the outline of our paper is that, first of all, there is the execution phase in which the parties run the initial passively secure protocol as it is without modifications. And after that, they execute the verification phase. This phase requires that it takes as inputs the computations that took place in the verification phase, the inputs and outputs that have been used there, and finally it outputs some message B to all parties, and it says, for example, Alice has cheated, but Bob and Chris are honest. So it verifies who exactly was cheating in this execution phase, so that it would be sufficient against the covert adversary. And in order to make this verification more efficient, we make use of a preprocessing phase, in which parties generate correlated randomness. And this randomness is used in the verification. So we do not use it in the execution phase in any way, although it can be done separately. But the preprocessing randomness that we have here, we use it only to make the verification faster. And now let us describe in more detail these three steps that we have here. So first of all, the execution phase. So it is almost not very interesting because the parties just run the initial passively secure protocol, HCTs. And only one small thing that we would like here is that all messages are signed by the senders. And why we need it? Because when we later do the verification, then we need to have to bind somehow the sender to the messages that it has sent to prove later whether there was some cheating or not. And everything goes fine as far as the parties indeed sign the messages that come. The problem is that what if a party refuses to sign a message? So one possibility would be that if there is some problem, of course, Bob can say that Alice has not sent me the message, I have not received the signature and the message, so there is some problem. One possibility would be to stop at this point, still we could verify all the rounds that took place so far before this round, which is not very nice because still the adversary can just abort the protocol and he will not be detected. So in general, we would like to proceed, but of course the message of Bob that I have not received them, which doesn't help because Alisa says I do have sent this message. So how it can be solved, and it has also been done in the related work. Here it is possible that Chris helps in the delivery of message, and he confirms that Bob received M and the signature on M. As soon as we have this honest majority, if there was a conflict between Alice and Bob, then Chris is honest, so he will indeed deliver this message. So it looks like it is strange we send a message now also to Chris, and why it is allowed, because if there was a conflict between Alice and Bob, and in this security model, it means that if there is some problem, then either Alice or Bob is corrupted. So the adversary has seen this message M anyway, and the adversary cannot learn anything new if we provide this kind of solution to message delivery. So this is about execution phase that finally provides signatures to all messages, but otherwise it is passively secure. And now comes the verification phase. And in this phase, this party, the prover, proves to the other parties, the verifiers, that it has behaved correctly in the computation. And before that, we assume that all relevant values have to be shared among the verifiers V1 and V2. So the messages M are sent either as M plus 0 or 0 plus M. It depends on who was on the other side of the computation, either Bob or Chris. So we use here additive sharing. The inputs also need to be shared additively, like x1 and x2, so no verifier alone can derive what is the value of x of this input. It remains private. And we assume it will be done somewhere before even the execution phase starts, when the inputs are already known. And finally, there is some correlated randomness that is also shared as R1 plus R2. It is known by the prover, and it has been shared in the preprocessing phase that we will describe soon how it happens. And we assume that all these shares that we have here, they're all signed by the prover. So Bob and Chris hold some shares and signatures on these shares. And now the verification itself is like reproducing the computation of P by using these additive shares that parties receive so far, and they use the correlated randomness. And let us do it on the example of multiplication. So Alice wants to prove that Z equals X plus Y, and all these values X, Y, and Z, they're already additively shared among Bob and Chris, among the verifiers. And how it happens, Alice takes some correlated randomness that will help it. For example, in this case, it takes beaver triples or multiplication triples, the random numbers A and B, and a product C of these two random numbers. And we assume that this correlated randomness is also secret shared among the verifiers, Bob and Chris. Then it computes some hints, and these hints are helpful because they help Bob and Chris to linearize the computation of this multiplication. And in this case, they do some computation with these hints and with the shares that they have, and it is easy to verify that if they compute this thing, it should be the value V that is shared among Bob and Chris, and it is supposed to equal to product of X and Y. And finally, they want to check if the value V that they got, it indeed equals Z. But of course, it works only if the hints are correct. So what they need to do, first of all, they verify the hints. And the second thing, yes, they check if this value V is equal to Z that was previously committed by Alice. So they verify if the multiplication was correct. And now the question is how they do these checks. The checks are very simple. They have computed some shares, and they want to check if the shared value is 0 or not. So the easiest way is just to open this value. But if you have two parties, they can do it even more easily or more efficiently, especially if there is a lot of such values that whose being 0 should be checked. They compute hashes of these shares Z1 and Z2, and why it works, because if Z1 plus Z2 equals 0, then it should be like Z1 is a negation of Z2. So they compute the hashes of these two values and compare if they are the same or not. And of course, if they do exchange the shares and compare if they are equal, then everything is fine, there are no problems. But if they are different, then there can be problems that the Chris doesn't know. Maybe they are different because Alice was cheating, something is bad with its shares, but maybe Bob has just sent something wrong instead of H1. And what happens here, if they are different, they just send this H1 and H2 both to Alice, and since Alice knows all the values that were used in computation of these values, she can check. And she knows who was cheating, whether Bob or Chris. And then she has a right to complain against one of the verifiers, for example, Bob was bad. And if there is a complaint, then Bob has to open all the values that with the signature of Alice to Chris, and the Chris can redo the computation and check. And if these hashes are finally equal, then Alice is honest and Bob was cheating, and if they're still different, then of course Alice was cheating. And again, we can do this opening because there is a conflict between Alice and Bob, so everything that Bob shows to Chris, it is known to the attacker anyway, so it doesn't leak any additional information to the attacker. And yes, Chris checks who was cheating, whether Alice or Bob. And we just were left with the preprocessing phase, how it happens, because we need to tell how exactly these triples are generated. And this is quite simple. The prover itself generates all correlated randomness because it is allowed to be known to the prover. It generates a lot of, for example, multiplication triples, and then each additively shares all these triples. And finally, these verifiers run some verification to check if these triples are correct. So there are some standard methodologies, like they open and verify if some triples are correct, so they discard some triples. And finally, they sacrifice some triples to verify that the other triple is correct. So these are some standard methods that are often used in triple generation. And again, they need to check if the value of 0, and they can do it similarly as it was done in the verification, and even simpler, because in this case, if it is preprocessing, it is not so important to identify who was cheating, whether it was Alice or Bob. So if there is some problem, we can just abort in the preprocessing phase, because preprocessing doesn't involve any private inputs anyway. And the covert adversary couldn't extract any private information. But of course, if we want, we could identify the cheater also here, similarly to the verification phase. And what is the main difference between how it is usually done, these preprocessed triples, that all these triples are known to the prover. And this allows to make this generation more efficiently. We don't need to write a secure protocol that generates these triples. And that's why we also can extend our preprocessing phase not only to multiplication beaver triples, which are highly optimized also in other works, but we can use some other interesting process tuples like trusted bits, or characteristic vector of some number, or rotation tuples like some random vector rotated by a random number, or even permuted by some private permutation. And their generation and verification is analogous. Prover generates all these tuples itself, shares, and we run cut and choose and pairwise check. So there are different ways that we can do here, and we can compute various preprocessed randomness. So, and then there is a summary of what we did in this paper. We proposed a generic method in general for achieving covert security under honest majority assumption. So everything that was shown here so far, it works under honest majority because everything that prover shared among the verifiers, if the verifiers collaborated, of course, they could recover all the secrets. So this works with honest majority. If we applied it to some particular platform called ShareMind, which is three-party computation relating one corrupted party, and it allows us to convert its passively secure protocols to actively secure, and with identifiable abort, so we know exactly who was cheating. And that's why it is also useful for both active and covert security, because it allows to identify the cheater. The overhead of the execution phase is relatively insignificant. We only provide signatures, and especially if there are highly parallelized computations with a small number of rounds, then the number of signatures becomes very small compared to the communication. And in practice, when we benchmark it, the bottleneck of this active security for ShareMind that we measured, it was generation of preprocessed tuples. So even if we could somehow reduce the signatures or improve our verification step, it seems that still the most important thing that we should optimize is how these preprocessed tuples are generated. And fortunately, since many other platforms or some platforms also deal with this tuple generation, we can also have some of their ideas that we could also apply in our paper to make it more efficient. And thank you for your attention.